Welcome to Module 4, Part 0 of Refrigeration Cycle. In this module, we are going to review refrigeration cycle as a closed steady system. The prereq for this module is Module 1, Part 0 and 1, which was covered a long time ago. So in this module, we are going to just go over what is a closed steady system, just to remind you, and how we can build a refrigeration cycle without going into any details. So let's begin with a diagram of a closed steady system. The system is closed, as you can see from the boundary. There is no mass going in and out. Again, the system is very generic enough, allowing heat and work transfer of different kinds. And you notice the governing equation in their general format. If it's a closed system, we know there is no mass going in, coming out. So the transport terms drop out from all this equation. And steady means the picture of the system doesn't change with time. A hot spot remains hot, a cold spot remains cold forever. And therefore, if the picture at each little local system doesn't change, the aggregate of them do not change, which means the total mass of the system, total stored energy, or entropy, they don't change. As a result, the unsteady terms drop out. The equations get very simplified. So for a closed steady system, we know this is the energy equation, and this is our entropy equation. Again, we have covered that in Module 1 with reference to closed steady system review. Now let's go and apply these equations to a refrigeration system. Consider this red boundary. This red boundary is our closed system. There is no mass flowing anywhere across this boundary. And what is a refrigeration system? Think of it like a black body, a black box that transfers heat from a cold temperature. Suppose the temperature here is Tc, and it kind of draws heat from this cold reservoir and transfer it to a hot place, which is a temperature Th. In doing so, it requires some network, which is shown here. Of course, it's fighting against nature, because the nature will have a tendency to make heat flow from the higher temperature to lower temperature, but we are doing just the opposite. And how can we make it possible? Well, if we can satisfy energy and entropy and mass equation, that's something, a device that doesn't violate any law. Therefore, that's definitely possible. Let's see how it happens. Okay, so mass is constant. Obviously, it's a closed system. It's a trivial equation. Let's forget about this. Let's apply the energy equation. Again, as you recall, we just arrived. Energy equation is what? dE dt, which is 0, equals q dot minus w dot external. So 0 equals, what is q dot here? Q dot h minus q dot c. And what is w dot external? That's negative w dot net. Why I put the negative sign? Recall the Wien-Heap convention. Work in is negative, and w dot net is a absolute positive quantity. So we have to put a negative sign to make it algebraic, w dot external, and this negative simply carries over here. So this is essentially q dot net. So we recognize that for any cycle, as in the heat engine, this equation is universal. Now, as far as defining an efficiency or COP of a refrigeration system, it is the desired energy transfer divided by required input. That's the definition of any efficiency. But for refrigeration system, it's called the COP, the coefficient of performance of a refrigeration system. The desired thing is q dot c, and the required input is w dot net. So q dot c is called the cooling load. A very standard terminology, which means cooling load means this is our desired load. This is our desired heat transfer. Why do we need the heat transfer? Our goal is to keep this blue space, the cold place, at a low temperature Tc. And what will happen if I keep a place cold, then there'll be a natural tendency for heat to leak into it. Not just heat leaking into it. For instance, there could be some legitimate reason, say inside your classroom, inside your wherever you're sitting right now. If you look around you, you'll find there are a lot of heat sources, maybe some electric lamps or your computer generating heat. So those contribute to the cooling load. To keep wherever you're sitting, that room cold, heat has to be taken out. So Q dot C, that's why it's called cooling load. It's essentially, if this much amount of heat is transferred into the system, we have to remove that much to keep this little blue space at steady state. So Q dot C is expressed in kilowatt, and sometimes a funny unit called a ton of refrigeration is used. A ton of refrigeration means about 3.517 kilowatt. A ton means, it sounds weird, it's kind of like light year not being a unit of time, but distance. Similarly, a ton of refrigeration is not really a unit of mass. A ton of refrigeration means if you buy a ton of ice, 2,000 pounds of ice, and put it in a room, if it melts over 24 hours, then it will be equivalent of removing 3.517 kilowatt from your room for an entire 24-hour period. It was in the olden days, this was the only source of refrigeration, a piece of ice. But right now, just if you remember that a ton means this, that's enough. Okay, so now we know what is COP. COP is the desired heat transfer divided by the required energy transfer, Q dot C over W dot net. And as you see, Q dot C, we can express W dot net as Q dot H minus Q dot C. So we can write this formula simply in this term. So both these formulas are used. And this formula is the definition of COP, and we will apply it for an ideal cycle, actual cycle, vapor compression cycle, gas compression cycle, you name it. Any refrigeration cycle, this formula will be valid. Okay, now let's do an entropy balance on the refrigeration system. Once again, I'm going back to the animation, 10A Carnot COP in this case. For the entropy balance, this is our system boundary. Entropy balance basically means we are keeping track of how entropy of the system changes. And here's the entropy balance equation. Again, to understand it physically, the left hand side says how is entropy changing in my system, which is 0 because the system is at steady state. And there are only two ways entropy can change. Because there is no mass coming in and going out, heat we know can bring entropy in. And how much entropy is heat bringing? The amount of heat crossing the boundary divided by the boundary temperature, which is Tc in this case. How much heat is going into how much entropy is now thrown out by heat? Again, the answer is the amount of heat going out divided by the temperature of the boundary, which is different. And finally, there is entropy generation, which means what? Friction. Any friction, any type of friction, physical friction, mechanical friction that we all understand, thermal friction, which happens when heat transfers over a big temperature difference, electrical friction, when electricity goes over a voltage difference, whenever a gradient gets destroyed. Suppose you put a drop of ink in water, the ink will diffuse, the gradient of concentration is getting destroyed, so which means there is entropy generation, there is friction, and these are called thermodynamic friction. When all kinds of friction is absent, suppose that your refrigeration system is ideal or reversible, then this is 0. So the entropy equation really ends up in 0 equals, and this term of course has to be broken up into different terms around the boundary. There are two different terms. Here entropy is going in and here entropy is coming out. So the difference between the two must be 0. In other words, the entropy going in equals entropy comes out. So it's just like energy equation. You keep track of energy. Here we keep track of entropy through the second law. And it gives us a very simple equation for an ideal or reversible refrigeration cycle Q dot C over Q dot H equals Tc over Th. Going back to the COP expression we developed from any cycle, this equation, if we divide the top and bottom by Q dot C, we get to this equation. And this, we substitute what we reduced for reversible refrigeration cycle or the Carnot cycle. That's why this is called the Carnot efficiency, Tc over Th minus Tc. It's a remarkable formula. Notice, it tells you a lot without going into the details of a refrigeration system. Just think, suppose you want to understand the performance of a refrigeration system. If you just know what is the cold temperature, which is very simple to answer. Suppose you want to air condition your room and you want to keep your room at, let's say, 10 degrees Celsius, whereas the outside temperature, let's say, is 40 degrees, or let's say 50 degrees Celsius. Let's take an extreme example. So the essentially, look at the denominator, it's 50 and Tc equals 10, so the difference is 40. Now suppose you say, you know what, I can live with a temperature of 20 degrees Celsius. In that case, the denominator becomes 30. As you can understand, the COP will jump higher if you can live with a little less temperature difference. It's inversely proportional to the temperature difference you maintain between the hot side and the cold side. So when you reduce your thermostat, suppose you are in an air-conditioned room and you can see, the temperature difference with outside is 20 degrees Celsius, but I can just live with 10 degrees Celsius difference. COP will become twice. Of course, this is for an ideal cycle, but for a real cycle kind of mimics the ideal cycle. Not just that, if you increase your cold temperature, your cooling load will go down, as you can understand, because if the room is less cold now, so the heat leaking into your room will go down. So you save both ways. So it's important to emphasize the importance of Th minus Tc on a refrigeration cycle. Okay, now that we have covered the basic formulas, let's go and solve a very simple problem from chapter 2.